Last week we had a look at solving definite integrals. So this week we're going to start looking at some particular uses of integral calculus, namely finding the area under and between curves. And then this will be extended over the remaining 2 weeks into finding volumes of solids and things like so, and power in circuits. So when we find an integral, particularly when we solve a definite integral, what we're actually doing is finding the area underneath or between the graph of that function and the x-axis. So we look at that function on the screen there. That function is y is equal to a function of x, and we got that shape. If we integrate between two limits, we're actually finding the area. So this area here is between the limits a and b, a being the lower bound, b being the upper bound. So that's that bit of the equation. So we find the area of that bit. If we then want the area of this bit, because that's underneath, we take it away. So that's between the limits b lower bound, c upper bound. And then we get this last bit here between the bounds c and d added on at the end. Yeah. Just going to add a page here. What we're actually doing. Hang on, I want that one pencil. There's our axis. Yeah. And if we've got a function here, like so, when we do, and this is y equals some function of x, yeah. When we find the integral of that function as times dx. Now, what that is dx is like if we take a slice somewhere in that curve of a rectangle and say it's got a width dx, the area of that slice would be its height times dx. Yeah. So when you what this sign here means is between the limits, let's say a and b, is sum up all the heights times dx, and it's doing that when dx is tending towards 0. So you're making the slice that you're looking at very, very thin. It's tending towards 0, and so you get a very accurate measurement of the area. If you do the integration techniques, you find the area exactly underneath that curve. Now, there are techniques in mathematics. We're not covering them on this module, but you would if you've done HND, where you actually, if you don't know what the function is, you can take a number of slices across there and actually estimate the area by adding the area of all those slices together. There's 3 different techniques for that, but we are not covering them on this course. I just wanted to make sure you understood it, you knew exactly what you're doing when you integrate a function. You are finding an area. Yep. Okay. So let's have a look at a problem. What we're going to do is determine the area between the curve x cubed minus 2x squared minus 8x and the x-axis. So we're going to find the area here, and we're going to do it. I'm going to find the area of this bit and the area of this bit. So we need to integrate between the limits -2 and 0 for that side, and we need to integrate between the limits of 0 and 4. These are the values of x at those points. Yeah. So what we need to do is say the shaded area, or the area, equals the integral between lower bound is -2, upper bound is 0, of x cubed minus 2x squared minus 8x dx. We need to subtract from that the integral between upper bound is 4, lower bound is 0, x cubed minus 2x squared dx. Yeah. So we got two separate definite integrals to solve there. Okay. So we'll do this one together. If I look at this top one here, if I integrate x cubed, what do I get? Marker. Obviously not. Anyone?
Hello.
You can't remember. We keep x, we add 1 to the index, and we divide by the new index. Yeah. Do x cubed over 3 minus 8 x squared over 2, which is 8 over 2 is 4, so it's 4x squared. Between -2 and nothing. Yeah. Take away, we've got to do the other integral, so it's going to be x to the 4 over 4 minus 2x cubed over 3 minus 4x squared between 0 and 4. Follow that? So if we take the top one, that's going to be uh, 0 to the 4 over 4 minus 0 to the 3 over 3 minus 0. Take away minus 2 to the 4 over 4 minus 2 times minus 2 cubed over 3 minus 4 times minus 2 squared. That's this one. Yep. And then do it in different colour. This one. So you're going to take away 4 to the 4 over 4 minus 2 times 4 to the 3 over 3 minus 4 times 4 squared. Take away, well, when this is 0, they're all going to be 0, aren't they? Because okay. So with your calculators, tell me what answer you get for each of these two, the green box and the blue box. So that's the area between that graph, the area shaded in green there, between that function and the x-axis. All right. So let's have a look at another one. If we got a graph of the velocity of a vehicle over time, in this case, the velocity due an acceleration. If we find the area under that graph, we've got time on the x-axis, and we've got velocity, v, on the y-axis. So we're doing meters per second is velocity, yeah, and we're multiplying that by seconds. So we got meters meter seconds per second. They divide out, and we're actually finding meters. Yeah. So what we're doing is, if we find meters squared, sorry, we're finding the area under this graph. We're actually finding the distance travelled in that amount of time. So if we start off at 0, if we have our limits at 0 and 2, if we find that area, we're finding the distance travelled in that amount of time. Yeah. So what we've got to do is find velocity, which is equal to, in this case, the integral between 0 and 2 of 21 minus e to the minus t times dt. That's the task. Yeah. So what's the first thing I can do with that integral? I'm just going to go on to a new page. So we've got the integral between 0 and 2 of 21 minus e to the minus t dt. What's the first thing I can do to simplify that a bit? This is distance travelled equals. We can take this constant multiplier outside the integral. So we can go d is equal to 20 integral between 2 and 0 of 1 minus e to the minus t dt. Now looking at this, we're integrating a constant minus a exponential term. So we do those separately. So we can say c d is equal to 20 times the integral between 0 and 2 of 1 minus the integral between 2 and 0 of e to the minus t, and that was dt. Close the brackets. Yeah. So when we integrate, t at 1, what do we get? Well, when we integrate a constant, the variable comes back. So it's t. It's like integrating 1 times t to the 0. We add 1 to the index, divide by it, so we end up with t to the 1, or just t. And we're going to take away. Now, hang on. Yes. Yeah. Oh. Sorry, that's my wife asking if the dog's been fed. Right. Anyway, where were we? Oh, when we integrate e to the a t, a in this case is minus 1. We bring the a down, and so we're going to have minus e to the minus t, and we've got 2 negatives here, so they become a positive. So it's t plus e to the minus t, all between 2 and 0. Okay, anybody not following that so far? So and then we separate the limits, 20, and then we've got 2 plus e to the minus 2 minus 0 plus e to the 0. Yeah. That comes out as 20 times, and the value of this one is 2.135. Check that with your calculators, please. And the value of this is 1. So that's 20 times 1.135 equals 22.7 meters to 3 significant figures. Please check that with your calculators. Make sure that's the result that you get. Anybody not follow that? Connor, are you talking about the last problem?
Yeah, he said that a while ago.
Yeah. No. Yay or nay?
No, I've got 82.5 as well for the green bit.
So I'm doing a fraction. Minus 0.1 times so for the video, the problem there was this is plus 2 on the end of this function, making all these plus 2x. Plus 2 times 15. 2 times, so that's 142.5. Right? Have a look at one more, and then I've got 2 or 3 for you to have a go at. That's similar. Okay? So if we've got 3 linear functions here. Y is equal to 3x in blue. Y is equal to 4 minus x in red. And 3y equals x is the green one. And we've got limits to look at. But if we can find the area bound by those 3 lines, if we wish to, by saying it's going to be this green area here plus this red area here. Yeah. And we can find the red area by finding this area here and taking that bit away. And we can find the green area by finding all of that area and taking that little bit down the bottom. away. Yep.
Yeah.
So our limits for these two areas, the pink areas as I've got them, are 0 and 1. And the limits for the blue area and the red area, so the pink area and the green area, 0 and 1. And the limits for the blue area are going to be 3 and 1. Yeah. So to find this, to solve this problem, we need to do the integral between zero and 1 of this 3x function take away y is equal to x over 3. That comes from the function as 3y minus x. So y is equal to minus x over 3. Okay, that's where that comes from. Dx. And we're going to add to that the integral between 1 and 3 of 3x sorry, 4 minus x. Take away x over 3 dx. So that's a bit muddled with all my, let me just take my colors off there. You can follow them on the video if you need it. So we're finding two areas. That one from that bit. And that one from that bit. Yeah. So we've got to do integral between 1 and 0 of 3x minus x over 3 dx. We've got to add to that uh, 3 and 1 of 4 minus x over 3 dx. Okay. Now, integrating the blue bit. So we've got, it's going to be 3x squared over 2, added 1 to the index divided by the new index, minus x squared, divided by the new index, we're going to multiply we're going to have 3 times 2 on the bottom, which is 6. Close the brackets, and that's between 1 and 0. And then we're going to add open set of brackets, integrate 4, we get 4x. Integrate minus x, we get minus x squared over 2. And integrate x minus x over 3, we get x squared over 6. Close brackets, and that's between 1 and 3. Okay? So then the blue bit becomes 3 times 1 squared over 2 minus 1 squared over 6. Take away, and they're going to be 0 because both terms have got x as 0, so it's going to be minus 0 in there. Close the brackets. That's the blue bit. And then we go green. So we're going to plus 4 times 3 minus 3 squared over 2 minus 3 squared over 6. Take away 4 minus 1 squared over 2 minus 1 squared over 6. All right. Now, please check it out. But I get the blue bit as 1 1/3 plus green bit as 6 minus 3 1/3. So I've done those two separately. Equals 4 square units. Does that check out, gentlemen?
Could you go back 2 slides?
Of course, to that one. Yeah.
Yeah.
Remember, please, calculus with angles and sine and cosine functions, your calculator must be in radians.